In this tutorial, we will learn how to run an independent samples t-test. Sometimes an independent samples t-test is called a between subjects t-test because what it means is that you have two independent samples for which you want to compare the mean from each one of those samples on a particular outcome variable and determine whether or not those two means are significantly different from one another. So the first things first, and that is that we need to do file, new file, R script if we're working in RStudio to open up our R script or our R script editor here. I'm going to use the hashtag to note we're doing an independent samples t-test in R for this tutorial today. The next thing that we need to do as always is set our working directory. And I can see that mine is actually currently set where I want it to be. It is my H drive R workshop folder here, but just for the sake of demonstration, I will use the setwd function and quickly type in my working directory. And again, the working directory is where you're going to be saving the data files that you'll ultimately read in or import into R. So mine is R workshop. Okay, and if I run this line of script here, make sure you include the two quotation marks around your pathway there. Click run, you'll see that I've set my working directory there. Now, what data file are we working with today? Well, if I go to my working directory folder here, we are going to be working with a file called training, evaluation, pre-post control. So training evaluation underscore pre-post control. To make sure I get the exact name of the file, I'm going to click on it and copy the name. And this way I can, in just a second, paste it into my read function that I'll be using. So that brings us to the next step, which is read in the data. And so we are going to be using the read underscore CSV function from the reader package. And so first, if you haven't already, make sure that you use the install.packages function with reader, the name of the package we're going to be using, reader with no E, all lowercase in quotation marks, and make sure that you've installed this package if you haven't already, or if you need to update it, maybe you haven't updated in the past month or so, be sure to do this install.packages again. Now I've recently updated this, so I'm just going to run just the second of these two lines. You may need to run both, but I'll run the second of two, which is my library function, which is going to bring up or access my reader package that I've already installed previously. So with my cursor on the same line as the library function, I'll click run, and we see here in blue down there that everything seemed to run successfully. So that means that I have it installed here. Now the next thing that I want to do is I want to come up with a name for the data file that we're going to be working with. And specifically, remember when you read in a data file from your working directory into the R environment, we are going to refer to it as a data frame. And specifically, when we give it a name and create an object out of it, we call it a data frame object. And so for short, for training data, I'm just going to call this TD underscore. You could call it whatever you'd like. And I'll use the left-handed arrow to note that I am naming to the left this object here. And so I'm going to use that read underscore CSV function. You could use another read.csv function from base R or read with a capital R from less R. However you want to read in the data, you can do it. But I'm using the read underscore CSV function here. Now in parentheses, I'll put the sole argument in quotation marks. And that is the exact name of that data file. And remember, I copied this previously from my working directory folder. It's training evaluation underscore pre-post control. Remember, this is case and space sensitive. And make sure that you put the .csv there at the end if it wasn't already included, so that it's clear that you're reading in a .csv file here, which stands for comma separated values. So let's click run here. And here you'll see in our global environment, we now have that TD data frame object. Let's click on it to inspect our data. Looks like we have 4 columns here corresponding to 4 variables. We have our employee ID variable here. We have our condition variable here, which has new and old levels. So half the people here, 25 of them participated in the new training condition, and the other 25 participated in the old training condition. No one participated in both conditions in this sample, which means that this is ripe for running an independent samples t-test because we have independent groups of people, those who completed the new training condition and those who completed the old training condition. Now, we are going to ignore the pre-test for now. For this tutorial, we're going to focus just on the post-test here. So we'll pretend that we just have the post-test data here. And we want to know whether post-test scores, the mean or the average post-test score for the new condition is significantly different from the old condition. And we'll use an independent samples t-test to do that. Okay, and it's always a good idea too to perhaps grab the names of your data frame using that names function from base R, just names, and put the name of your data frame object as the sole argument and run that. And you'll see here we can copy and paste these names into our functions in just a moment. Other thing that's a good idea to do is to look at the structure. So str is another function from base R. If we type in the parentheses just the name of that data frame object, td, that we created and read in a second ago, and run that, you'll see that we have 4 different variables here, 3 of which are of interest to us. Well, really just 2. The condition variable, which is character. So this is appropriate for using independent samples t-test and using this condition variable as our predictor variable, or an independent variable, if you will. And then we have our outcome variable here, which is numeric in nature. Okay, so the next thing that we're going to do is we need to test the statistical assumptions for actually running an independent samples t-test. So although, for example, a post-test only with control group design is predisposed to being analyzed using an independent samples t-test, that doesn't necessarily mean that we've met the assumptions to run an independent samples t-test. The assumptions are, the first one is that you have normal distribution of the outcome variable for each level. So what this means is for each level of that predictor, each level of predictor here, I'll type that in. And so what this means is that you'll see a normal distribution for that outcome variable, which in this case is post-test scores, for each level of the predictor variable, which in our case is that categorical nominal predictor variable, which is condition, whether or not people are in the new versus the old training condition. Okay. So the second one is the equality of variances between our 4 outcome variable for each level of predictor. Okay, and so what this means is that not only do we want to see a normal distribution of the outcome variable for each level of that categorical predictor variable or nominal predictor variable, but we also want to see that the variances are equal, more or less, between each level of that categorical or nominal predictor variable. So one of the first things that we can do is to visualize the 2 distributions. And this isn't by no means a stringent test, but it does give us an idea. We can eyeball this and see if we're about in the ballpark of normal distribution as well as equality of variance assumptions. And then subsequently, I'll show you how we're actually testing this statistically, these 2 assumptions. And so what we'll do is, if you haven't already, use the install.packages function to install the lessr package. Make sure you put lessr with a capital R in the quotation marks here. And I've recently done this, but just know that this is a package that doesn't update relatively frequently. And so this, if you haven't updated or reinstalled this, let's say in the past week or 2, I recommend doing so now. I am going to use the library function with lessr, the exact name of the package, without quotation marks as the sole argument to access that package, because there actually are 2 functions we'll use from it today. First is the plot function to look at these distributions, and subsequently we'll actually use the ttest function from this to run our independent samples t-test. Okay, so let's use that plot function with a capital P from lessr. The first thing that we're going to enter is the variable of interest for which we wish to see the distribution, and this is going to be our outcome variable, which is our post-test scores. So that's post-test with a capital P and a capital T, as you can see there. And then we need to note that that's using the data equals argument, that is from the TD data frame. So remember, this is our TD data frame here. Okay. And then finally, we want to actually do a by argument here, and it's specifically the by equals, or the by 1 equals argument. And we need to say, well, how do we want to split this independent, or this outcome variable, this post-test variable, And specifically, we want to split it by condition so that we can test the two statistical assumptions here, because we're interested in normal distribution of that outcome variable and the equality of variances for the outcome variable by each level of that predictor variable. So the by equals 1, by 1 equals, we are going to put the name of that categorical or nominal predictor variable, which is condition here. Okay, and I'm going to open or enlarge this window a bit more so that you can see it over here. And I'm going to run that line of script. And so here you can see that we have on the y or the x-axis here, we have the post-test, which is our variable of interest, our outcome variable interest. And then we have the two levels here. So this is a trellis display, and we can see the two levels are new versus old training conditions. And we can see roughly, yeah, these distributions look about right. They look about equal here, okay? So the next thing that we're going to do is we are going to run our independent samples t-test, because at least initially looking at this, we can see, well, okay, this looks like the distribution is about normal for each one of these, new versus old, and the variances look closely, relatively closely similar to one another. Now, so when we run the independent samples t-test, we actually get statistical test of these two statistical assumptions built into the function from less-r. So it's one of the advantages of using the t-test function from less-r. And so to use this function, we are going to just type in t-test, all lowercase, t-test, and this is from the less-r package, so make sure that you've accessed it, which we did above. And then we need to first, as the first argument, specify the name of the model that we're testing. And so the t-test model we are going to specify is post-test. So this is our outcome variable, tilde, which separates our outcome variable from our predictor variable. And our predictor variable is that categorical condition variable, okay? And so the way you need to remember this is that to the left of the tilde is your outcome variable, and to the right of your tilde is your predictor variable. And so we'll add a comma here so we can add an additional argument. The next argument is that we are going to add data equals, and again specify the name of the data frame object, which is TD. So we read that in earlier, and that's what we named our data frame object. And then finally, we just need to do paired equals false as our last argument. And this is saying that the data are not paired. In other words, the data are not dependent on one another. Okay, so for example, they're not repeated measures, or every case does not go through both conditions of this particular training program here. So what this is saying is that we're actually running an independent samples t-test here, in other words. So make sure that you include that there. It is the default, but it's nice to specify it like that. Okay, so click run. And so yours will look a lot prettier than this, but you do get a nice little graphic here that shows the two distributions that you're comparing, and these are for the two means. And yours won't be overlapping like that. Now, the next thing that you're going to do is you're going to take a look at your output down here. This is where all the information that you'll be interested in lives. So let's scroll all the way up to the top. You can see that we're comparing post-test across condition levels, new and old. Okay, so that's what we're doing with an independent samples t-test. This is important, this first section that's called description. You get the number of cases or observations for each level of that categorical predictor variable, which is condition new versus condition old here. We see we have 25 people in each condition here. And then in addition, you can see the means here. We have 72.36 for the new condition. So this is the post-test scores for the new condition employees, and 61.32, and this is the post-test scores for the old training condition. And so just eyeballing this, we can see that, yeah, those means look different, but that's just descriptive. Our question becomes, are these statistically equivalent or statistically different from one another? And then you also get the standard deviations for both. And you also get the raw sample mean difference of the post-test, which is just simply 72.36 minus 61.32 is 11.04. And you also get the within group standard deviation below. Now, as I mentioned, we also get automatically through using the t-test function from less-r, which is again one of the advantages of using this particular t-test function, is you get your statistical assumptions tested with statistical tests. So, whereas before we were eyeballing, so if we go back to our plots here, might be a second, but we should see that, well, it looks like it's disappeared here, but typically you would see the there we go. you would see that we've eyeballed the statistical assumptions here about normal distribution for each level and equality of variances across levels. Now, here we have a statistical test. So here we have the statistical test for the assumption of normal distribution for each level, and that is the Shapiro-Wilk normality test here. And so you get the test statistic here, but what we're really interested in is the p-value. Now, the null hypothesis here is that each distribution, each variable we're looking at, or each level, the outcome variable for each level of that predictor variable, we're looking to see whether or not that's a normal distribution. And the null hypothesis is that the distribution is normal. So this is an interesting case where we're actually don't really want, if we want to run an independent samples t-test, we don't really want these p-values to be statistically significant. And here we see that our p-value for the new training condition for our outcome variable, the post-test scores, is 0.253. So this is definitely greater than our typical two-tailed alpha level of 0.05. So we would fail to reject the null hypothesis. In other words, we're saying there's really no evidence to suggest that this distribution is anything but normal. And we see the same thing here for the old training condition in terms of that post-test outcome variable, its distribution. We see that the p-value is 0.621. Again, this is greater than our traditional or conventional alpha of 0.05 two-tailed test. And so therefore, we also fail to reject the null hypothesis that this distribution is normal, which means that we have no evidence to suggest otherwise. And so we're going to assume that these are two normal distributions here. Now, what about that equality of variances? Well, there's a couple tests here. The one we're going to use is Levine's test here, which is fairly common. And Levine's test tests that equality of variances assumption between the two levels of that predictor variable for that outcome variable that we're interested in. And so here we get our test statistic, degrees of freedom. But what we're interested in here is the p-value, which just like Shapiro-Wilk normality test, the null hypothesis is that these variances are homogeneous or equal to each other. And so in this case, again, if we would like to meet the assumption that we have equality of variances, we actually want this p-value to be non-significant. Okay, so here the p-value is 0.344, which is definitely greater than 0.05, which is the conventional alpha two-tailed test. And so what we would say is we failed to reject the null hypothesis that the variances are equal or homogeneous. And so what this means is we have no evidence to the contrary that would say we need to assume that these are unequal variances. In other words, we can feel confident that we have met the equality of variance or the homogeneity of variances assumption as well as that normal distribution assumption as well. So what this means is we can now proceed forward with the inference section here. And we are going to look at the section where it says assume equal population variances because we met that assumption visually using the plot as well as the Levine's test here. Now, if you had had a significant value, meaning p was less than 0.05 for Levine's test, then you would come down to this section that says do not assume equal population variances. Okay? So what we're really interested in here is this line, the hypothesis test of zero mean difference, or a null hypothesis here is that there is no difference in the two means or averages in terms of post-test scores for each level of that categorical predictor variable, meaning new versus old training conditions. And so here we see our t-value is 4.798 and degrees of freedom are 48, and our p-value is 0.000. So this is a very small p-value. And so what we can conclude is that indeed this p-value is less than 0.05, which is the conventional two-tailed alpha level. And because our null hypothesis is that there is no difference between the means, what we're doing here is we are actually, because this is a statistically significant finding here, the p-value is less than 0.05, we are going to reject the null hypothesis that these two means are equal. In other words, we conclude that there is indeed a statistically significant difference between post-test scores for those who participate in the new training condition versus those who participate in the old training condition. Now, how do we know which one performed better? Well, that's where you can scroll all the way back up to the description here, and we see, yes, it was those in the new training condition who had a mean of 72.36, whereas those in the old training condition had a mean on that post-test of 61.32. So we would conclude that indeed there appears to be evidence that those who participate, those who go through the new training program will have have statistically significantly higher post-test scores on whatever it's assessing than those who were in the old training condition. So it seems to be that the post-test worked better, and this is how we're evaluating that post-test only with control group design. Now, if we scroll further down, you'll see there is also a section called effect size, which is also a nice attribute in the output as far as this t-test function from less r goes. And so what we see here is that we get an estimate of practical significance, which is our effect size, and we see Cohen's d, which is the standardized mean difference, as it notes here, for our post-test. So it's how big of a difference is that in standardized units? And what we see is that it's 1.36. Now, conventional cutoffs for Cohen's d is that small is about 0.2, medium is about 0.8, and large is about, medium is about 0.5, and large is about 0.8. We can see this is definitely larger than 0.8, so this would be a large to very large effect size here. So in terms of practical significance, this is probably, not only is these two means different from one another, but we can also conclude here that practically this is a pretty large difference. So it seems like this new training program is substantially better than the old training program, at least when we're evaluating it on this particular post-test outcome variable of interest. Now, you can scroll down here and there's not much else that we're actually interested in the rest of the output here, but you get all this valuable information. Now you could also run a t-test, for example, using the t.test function from base R, but you would also have to run Levine's test, Shapiro-Wilk normality tests as far as testing statistical assumptions go separately. And then you'd also have to run a separate function. There's a different packages that can do this if you want to actually assess Cohen's d, or estimate Cohen's d as an indicator of effect size and practical significance. So there's always, of course, different ways you can do this. And in the written tutorial that corresponds to this, you'll see how to actually run a t-test using base R functions, as well as some other functions from other packages. But here, the t-test function from less R packs a lot into it. It makes it kind of a one-stop shop here in terms of the statistical assumptions and getting your statistical test of the hypothesis, as well as your practical significance test as well, which is your Cohen's d. Okay, so this sums up how you can actually run an independent samples t-test. Now, what if you want to visualize the outcome? Okay, so what if we want to show, because we found a statistically significant difference, at which point I should note too that conventionally, if you find a statistically significant difference between the means based on the t-test and its associated p-value, then you would proceed on to interpret the effect size or practical significance. If you didn't find a statistically significant difference, then we're treating these means as no different from one another. In other words, we're treating them as equivalent, so you wouldn't go on and interpret how big of a difference is there, because you've actually established that there is no difference there, at least from a statistical significance standpoint. The same thing goes for as far as presenting a data visualization. Often I think it's most responsible to only present a data visualization of such results if you do find a statistically significant difference, and one in which you consider to also be practically significant as well. Okay, so we're going to create a bar chart now of the results, and this is actually going to be a two-step process. So the first thing that we need to do is we need to create actually a vector of means that we can use as input to another function, the bar chart function we're going to use. And so we can call this whatever. I'm going to just call this post-test underscore means. This is just the object I'm going to create that's going to be a vector of means. And so how do I create that vector of means? Well, I'm going to use the arrow function here to name this vector, saying that this is the vector of means I'm calling post-test underscore means. And to the right of it, I'm going to specify how I'm going to create that vector, which is using a function from base R that's called tapply. Okay, and this allows us to apply a certain function to different levels of one variable relative to another continuous variable. So the first thing we want to do is specify the name of our data frame followed by $sign to say that this is our continuous variable or outcome variable of interest in this case, which is post-test, and it belongs to the TD data frame here. And again, we use that $sign here to attach these, and you might be familiar with this already. Then we add a comma, and our second argument is going to be the categorical variable. In this case, it's our categorical predictor variable from our independent samples t-test, which is that condition variable from our TD data frame. And so again, TD $sign and the exact name of our condition variable, it's condition with a capital C here. And then finally, our last argument, so we add another comma there, our last argument is the mean function, MEAN, all lowercase, from base R. So what we're doing here is we're saying apply the mean function to post-test this continuous outcome variable for each level of this variable here, which is the condition variable. Okay, so let's go ahead and click run. Oops. Sometimes when I have this blown up, we get little error messages there. So I'm clicking run there. So this is something, if you blow up the view like this, sometimes it confuses RStudio. Even when you're ostensibly not running a plot, it'll actually confuse. And so sometimes this solution is just opening up the window so the whole visual can be displayed there. Okay, that likely won't be an issue because you're probably not blowing up the screen using view and zoom in as much as I am for this tutorial. Okay, so now what we've done is we've successfully created a vector of means. And so you actually just highlight this vector of means, post-test underscore means, and click run. You'll see that we have new, old. So this should look familiar. This is the mean for post-test scores for the new condition. And this is the mean for the post-test scores for the old condition there. Now we can use the bar chart function. And this bar chart function comes from lessR. So you need to make sure that you've accessed the lessR package before using it. And so we need to type in the exact name. I'm just going to copy it here, post-test underscore means, as our first argument. This is the vector of means we're going to use as input, and then comma. And the next thing, I'm going to just hit a return or enter so I can go to the next line here, but it's all going to work the same in the same function because it's within the parentheses. Next thing I want to do is I'm going to use xlab for label the x-axis, and I'm going to say training condition is the name, and you need to make sure you put that in quotation marks. Add a comma afterwards. And so that'll specify the label for the y-axis. And then I'll use ylab equals to specify the label for the y-axis. So x-axis here, y-axis here. And for the y-axis, I'm going to say average post-test scores, all in quotation marks. Okay? Now watch what happens when I run this. Okay, so you'll see that we have relabeled the x and y axes. You get the level labels here. So new versus old for that training condition. Here are the average post-test scores. But notice that we get this. These percentages actually don't make sense here. This is just the default by lessR. This would be if you were doing a count. We're using means here. And so to get rid of that, we can actually add another argument by adding another comma and then doing values equals off. And so this will silence these two percentages here. So let's rerun and make sure you put off in quotation marks there. Let's rerun this. Okay, now those values are gone. Now, if you wanted to do some additional stylistic, taking away the grid lines, for instance, you can use the style function from lessR and use the comma. You can use the question mark here if you want to see what the different arguments you can use. And so here we want the style from lessR. And you can scroll through and there's so many different things that you can do here to refine your data visualization. And so you can check out, all you need to do is run whatever style function you have in the arguments before you run the bar chart function. And if you want to turn off the style again after you run the bar chart, just do a style function without anything in the parentheses here. Empty, no arguments. All right, so this wraps up the tutorial on an independent samples t-test in R. Thank you very much.